Okay, so I think we can get started. So let's get started, right? Some upcoming due dates. Quiz 3 was due as of last night, and quiz 4 is also now out. Same thing, four-day work time. The slides aren't on the screen. Yeah, the slide should be on Canvas. Yes. And quiz 4 is also now out, so we're also having that due on next Wednesday, so that it doesn't collide with next Friday's due date for programming assignment 2. Where are we heading with all this? So we're heading toward 3 weeks now until spring recess. So the things that we want to get done by spring recess is let's make sure we're done with studying data representation, so integers and floating point. And also the third programming assignment is also going to be collected before spring recess. So all of these units, C programming, memory, arrays, allocating memory, freeing memory, the heap, the stack, integers, bits and bytes, floating point, these are the material that will be on the midterm when we get back from spring break. And again, right, the best way to prepare for the exams in this class are the quizzes. The quizzes really give you a sense of the types of questions I like to use to assess in exams. So one thing that we're also going to be doing in recitations this week, and then some of them in next week, are code review. So the idea is that when we have classes like this where assessment of code is basically based off of automatic grading, you don't get as much feedback as you need on what is good code, right? Writing code is as much an art as it's just about getting it to be correct. And so the TAs will be pulling up examples of good quality code where the code is very readable, it's got good structure, sensible variable names, and also some examples of bad quality code. And you'll take turns kind of assessing and kind of chiming in on what makes for good code and what makes for code that is difficult to maintain. Yeah, you have a raised hand?
Yeah, going back to quizzes, you say that there's going to be quizzes are the best source for you to take the exam. Does that mean the exam is going to be majority multiple choice?
The exams are all multiple choice. Yeah.
Would it be possible to, after like all quizzes, because like all the quizzes have been like submitted, would it be possible to like at least like what the questions are so we can look at them?
The quizzes should be visible to you even now that they're collected. Let me know if that's not the case. But yeah, the quizzes remain open all the way until, for you to view all the way until the end of the semester. Yeah. No notes for the exam. Exam is closed books, closed notes, closed electronic devices. Okay. So I want to have this discussion about, what are the kinds of techniques and kind of skills that we want to have to develop in programming for this class, right? The kind of programming that we do in 211 is somewhat harder than in 112. C is a language that is more difficult to work with in the sense that more things could go wrong. Sometimes the error messages that it gives you are nonsensical. And knowing how to manage memory, where to allocate memory, where to free it, all of this it takes a lot of experience. So kind of some key takeaways, right? One of the most important things about programming I'm hoping to cultivate from like these programming assignments is that it helps a lot to head into writing your program with a plan, right? So before you even start writing code, oftentimes a good thing to do is to write down a set of notes to have a plan on what you're trying to do. If you've got test cases, open the test cases, open the answer, expected answers for those test cases, work through by hand so you can explain why the expected answers are what they are. And one very specific thing is to never try to code by trial and error. Right? Who's gotten into this loop before? The code doesn't work, so let's just randomly move some code around and kind of test different things until finally somehow it magically works. Right? We've all been there. I've been there. And one skill that you need here is the ability to debug, right? To know what you need to find out, to know exactly what's going on in your program, right? A lot of printouts using the debugger, really getting a lot of view, a lot of insight into the state of your program is very valuable. And then kind of one of the things that we want to do with the code review is to give you opportunities to read more code, right? And that's another thing we do in this class. I upload a lot of example files into the shared repository. All of that is for me to use here in class demos, but also a lot of it is for you to study and understand how it works. Here's a slide that I really like. This is borrowed from a course offered at Yi-Peng that I've seen in somebody's talk before, and I'm excerpting here. This is a class that's about code correctness, and it's somewhat kind of similar to a software methodology course. But it really highlights how having good programs and high quality code that is correct, that is high performance and secure, is a system of mechanisms, right? It's not just about debugging and using printf statements. So I kind of want to have you take a look at this slide here and maybe point out some of the practices that we are using for these programming assignments that correspond to what you see on the slide there. You have a hand raised?
Sorry, did you turn the lights off?
Oh yeah, good call. So what are practices that we use in this class that you identify with what's being showed on the slide? Yeah.
Compiler flags.
Compiler flags, so what do you mean by that? Yeah, so as a default within the make files that I give you, the compiler flags, GCC is configured to warn on all possible mistakes. And then in fact, if it's a warning, it gets escalated into an error and compilation stops. Right? And you'll have software engineering teams out there who consider using this set of flags to be way too onerous, right? They're willing to compile code that has dozens and thousands of warnings flying by. And so long as it works, right? In this class, we crank up the pedantic correctness that the compiler can offer you so you build good habits writing code at the get-go. So what does that correspond to maybe on the slide here? Yeah, so that's definitely a set of technological tools. It's, there are these things called lint tools that just look at the code, right? Without even compiling or via compiling the code without running the code, can detect whether or not the code has bugs in it. What else? What other practices? Yeah.
We have methodological approaches because we're given test files, so you can run code, see how many test files are passed, which ones aren't, what are the comparisons between them, what are the similarities between test files.
Yeah, so there's a methodological aspect here. We use test cases, and then furthermore, what about the test cases?
There's a lot of variation between them. It's not just like, the same number of lines. There's a lot of varying numbers as well, so you can want to cover cases.
Yeah, so there's randomized testing. The autograder will generate a lot of increasingly large and challenging test cases. The autograder knows how to calculate the expected result. And it subjects your program to a huge variety of different test cases to try to hit the corner cases, right, to reveal potential bugs that you haven't thought about. There's a kind of another aspect to this approach. In some sense, the autograder is written in Python, so there's a kind of cross-checking here. It's harder to make the same mistake twice in two different languages. Right? The autograder is written using Python libraries, and your code is written in C, and between the two, it's likely that the same mistake doesn't get made twice in two different programs by different programmers in different languages. What other practices that you see on this slide? Yeah, go for it.
Bug tracking, whenever we compile a code and run it, they have the summary at the bottom, tells you which lines are wrong, what the errors are, so you can track that and fix your code.
Yeah, so that's a kind of bug tracking. So the error messages will tell you where in the line of code, in the source file, is the bug emanating from. But bug tracking more generally refers to something like GitHub. It has this ability to file bug reports and via version control of the file, maintain versions of code that work out the bugs over time. Right? And we actually do some of this too. Sometimes there are mistakes in the auto-grading framework that are released. Somebody posts a question on Piazza. I realize, oh, there's a mistake here. And I can push a patch, right? Everybody pulls again, and then the auto-grader is patched. What other practices? Right, so in recitation, we're going to do code review, where you can study good code and bad code and learn about what is high-quality, maintainable, readable code. We definitely do randomized testing, where test cases are randomized and you're tested against dozens, if not hundreds, of different input sets. And then down here, what is a sound type system? So the languages that you're familiar so far, Java and C, are very strongly typed, right? They have very strict grammars about every variable has a type. And the operations that you can do between variables is dictated by the type system. So by nature, by programming in C, you're programming a language that offers help from a type system. Now, what's a language that is not so strongly typed? What would that look like? Yeah. Yeah, so if you have experience in some other languages like JavaScript, Python, Perl, some other very popular languages, when you declare a variable, you don't have to know if it's an integer or a floating point or an array or whatsoever, right? The program does its best to figure out what the type is. It's more convenient, but there's a lot of opportunities to make mistakes, right? Because you don't have the help of the compiler figuring out whether or not the operations you are doing make any sense on the variables that you declared. Good, so this is just kind of pointing out some of the things that we're learning intrinsically through the programming assignments. So on Tuesday, what we did was we worked through bits and bytes. So we worked through the representation of numbers in different number systems, binary, octal, hexadecimal. We did some exercises in converting between them. We did some exercises on figuring out the colors relating to hexadecimal color codes. And at the end of class on Tuesday, we had a demonstration of an interesting way to swap two variables. And so just to pick up from there, this is a code that demonstrates you could swap two variables by just performing purely XOR operations. Right, so who recalls doing this on Tuesday and wants to give us a quick walkthrough of how this works? Yeah, you want to give it a try? Or?
Like you have two integers which are represented in binary,
Yeah, so it's flipping bits, right? It's flipping bits following the rules of XOR so that at the end of all of this, somehow the variables get swapped. And so we work through how this is so. Every line of code, you can think, okay, after this line of code, Y will store whatever this value is. The next line of code, X gets assigned this calculation, but what's Y at this point? This Y at this point is going to be, in parentheses, this. And XOR is a associative operation, so we can move the parentheses around. We can re-parenthesize it. All that is equivalent to this. And if you look at what X XOR X, what is that always going to be? A XOR A. A XOR X is just, yeah, so I actually need to pull up Tuesday's slides, right? 213. Yeah, so I need the truth table to show you all. So Tuesday's slides, we've got the truth table for XOR. So what happens if you plug in on this truth table here, A XOR A? So you just have to follow these two rows, right? The rows where A and B are the same, the result is 0. Or if A and B are the same, and in this case 1, results 0. So something XOR, bitwise XOR itself is always just going to be 0. So this simplifies to 0. And then what happens when you 0 XOR something? So back to the slides. Suppose you have 0 XOR B, well, the result always just follows B. So it just simplifies that again to Y. So successfully already, Y is stored in X. And then what's the next step? The last line of code, we can work through what happens. Right, so that's what the line of code tells us it will do. But at this point, we know X has been plugged in to be Y. And what's this going to be? What did we do wrong here? Hold up. Ah, good call. Sorry about that. Very good call. So yeah, what is Y at this point? Right? Y at this point stores this value. This operation is commutative, so we can reverse the order. And associative again, so we can re-parenthesize. Good. So again, Y XOR Y, that simplifies to 0. 0 XOR anything, that simplifies to X. Right, so this is how we see that the two values, by just performing bitwise operations, you can swap the two variables. We also need to talk about the other kind of review aspect. What's up with all of these pointers? Why is this all done using pointers? Yeah.
Because if we just grab the integers, it won't be saved into our main function, so the values will actually change because we're working into the area of memory.
Good, right? So one argument that you can think through it is by passing in pointers. This is like passing by reference, allows the swapping in the variable get reflected out in the main function. What's another way we can think through it? When we're swapping, where is this Y variable and where is this X variable actually located in memory? We can narrow it down, right? First of all, it must be what part of memory? The heap? Okay. No, it's in the stack, right? It's in the stack. So in our worked examples, it has roughly addresses that begin with what? 7 something, right? Something on a higher range of the memory addresses which correspond to the stack. And then within the stack, how is the stack organized? The big chunks of the stack are called function frames, function call frames. So we've got here 2 functions. So we've got the main, and then what we call in-place swap. In-place swap's call frame gets put onto the stack. But in terms of where y and x are stored, they are always stored back in the main, right? They belong to the main function's call frame, so that even though in-place swap is playing around with the variables, the data is being reflected in the main. So when in-place swap runs through, it returns void, the whole stack frame gets popped off. In the main function, A and B are successfully swapped. Okay, so who thinks that doing this is a good idea? Right? There was a question on the Zoom chat when I showed this on Tuesday. So why didn't we do in-place swap using this? Isn't this more elegant in some way? Yeah, what's your opinion?
It's more logically complex, like you can make lots of mistakes with it rather than using a temporary variable.
Yeah, so in our swap pass by reference example, we just declare a temporary variable, right? We just hold on to x, we put x into temp, put y into x, and then put temp into y. That works perfectly fine. There's a very subtle thing where this will fail. I'm wondering if anybody will see it, yeah.
Doesn't this only work with integer values or values that can be represented by binary?
So this only works for integer values and only values that can be represented by binary. So that's a good way to think about it, but what's a counter example? So you say this only works for things represented as binary. That can be represented as binary. So what's a counter example? What's something that cannot be represented as binary in a computer? Okay, so your claim is,
I think a string would be better than a character, but yeah.
so we'll change the types here to just be characters. A and B, and these are all now character types.
Actually, sorry, can't characters be represented by binary because they can be represented as their ASCII value?
So let's experiment, right? So what do you think will happen here? The claim is I'm hinting that there's something wrong that wouldn't work here, and one candidate is this might not work for something that's not represented as binary, right? So who thinks that this will succeed in swapping? Some hands. Who thinks it will not succeed in swapping? Okay, some other hands. So let's find out, right? So did it succeed? And why did it succeed? So far I've been saying that we can do this bitwise operations and it will work through it. And here, characters are not obviously numbers, but so why did this succeed? Yeah.
Those characters can be represented as integers in.
Yeah, ultimately, according to the ASCII table, all the characters are really just binary numbers stored in the memory. So you can still bitwise operations on anything that's a binary number. So it's not that, right? So it's not the fact that potentially characters can't be swapped. There's something else about this code that is subtly wrong. Would it work if we have a signed int? Okay, so we can try that as well. Not singed. So as a matter of signed ints, we can say, well, let's just make it both 2 negative numbers. That should be fine. Compile and run. So no problem. I can swap it just fine. Yeah.
Would it just work
So it worked for primitives, but not for non-primitives. So we can go through any iteration of this. I can change this to be pointers to pointers, right? I can try to swap pointer values. It'll show that it'll swap pointer values no problem. The subtle thing is, yeah. Is there a problem if x and y are equal to one another? So how do we find out? Right, so one claim is, okay, if they are equal to each other, say like this, right? A and B are both 2024 now. Well, we could run this program. The expected result is still correct, right? Swapping 24 with itself is the same. But we're getting closer. What's another thing that could fail here, right? The answer is if I try to swap a variable with itself. Right? Now I'm just going to completely get rid of any mention of B. And so what I'll try to do now is I'm going to swap A with itself in memory. What's going to happen now? What's the expected result? I'm swapping A with itself. Yeah.
Well, I guess expected nothing would happen.
Yeah, that A gets swapped in place with itself. A should stay the same. But what's actually going to happen? Yeah.
Is it going to null itself out?
It's going to null itself out, right? Because A XOR A is just 0. So if we run it now, after trying to swapping them, it cancels itself out, right? So this is a very good reason why this is just kind of a neat trick, which is not used in practice. But the main point here is bitwise operations are cool, and here's an example of that. Okay, so let's rewind all this. And we'll go back to our slides. So we studied in-place swap just now. And a important just reminder of all of this is to not to confuse bitwise operations and logical operations. So I'm going to do a little demonstration here in terms of what happens if we use the not operator for logical values on different types of values. Right? So when you see this character, the exclamation point, what does that usually mean? Not, right? So what can you apply not to? To bools. Good. So do not operators only apply to bools? Yeah.
We apply it to conditionals like not equal to.
You can apply to conditionals like not equals to. Right, so what I'm going to do here in this example code is a little study, right? I wanted to show two things. One thing is all variables, any number, any data type, has associated with it a truth value. Right? So Booleans have truth values. Booleans can be true or false, but actually so can everything else. Right? Is this true in Java? So some nods. Who's thought about this? So who's uncertain? Okay, right? This applies to C and in Java. Any variable has a truth value. And what does that mean? I'm going to say any variable whatsoever can have a truth value. Yeah.
Is it null, or does it have like a value associated with it?
So what I'm getting at here is even A, right? Here A is an unsigned integer. This is not a Boolean, right? A is now 0. I can inquire, is A true? So here there's another little snippet of code that I just want to pause on too, right? What does this snippet of code mean? Yeah. Yeah, so this is called like a ternary Boolean operation, Boolean evaluation, right? It's a little syntactic sugar, right? This is just a very commonplace shorthand that is useful in C and is also correct in Java that says, is A true? If true, then print true. Otherwise, print false, right? And this line of code here saves us maybe probably 3 or 5 lines of code all condensed into one single line. Okay, so what's this going to print? What do you think this will print? Any guesses? Yeah. It'll print true. Who think it'll print true? Who thinks it'll print false? So the falses have it, right? So what's happening here? It's looking at A, and the assignment of the truth value to any variable is that if the number is 0, then it will print false. Yeah, and what if it's something else?
What if you declared A but you didn't initialize it?
What if you declared A but did not initialize it? Okay, let's get to that later. First, I want to talk about what happens if A is something else, right? What's the truth value of the number 211? What do you think the program will print now? Just shout it out. Yeah, so it'll print out true, right? Because 211 is not 0, so this will be evaluated to a truth value of true. What if A is declared but not initialized? Well, let's give it a try. I think it's undefined, but here it's telling me it'll print true. Good question, though. Yeah, interesting. Okay, so let's roll back some more. So furthermore, A has a truth value. And so it's possible to negate it. Right, so if A is 211, in this line of code, I can negate 211. So what does that mean here? Yeah. So this is the little trap that I want to avoid here. So this is what this slide here is emphasizing, right? The distinction between bitwise operators and logical operators. So bitwise operators, by what the name calls it, it will go through the bits of a number and perform that on every single bit, right? So if we applied tilde on 211, indeed, it will go to the number 211 and flip every single bit of 211. But that's in contrast to this here, right? The logical operator. So when we have a logical operator, what it does is it treats the number and evaluates what's its truth value, right? And what's the truth value of 211 again?
False.
True, we printed just now, right? 211 is true, and so not 211, what is that? False. And then we're going to print false as a integer. So what's a reasonable thing that I should print? 0, right? So indeed, GCC logical, run it, prints 0. What if we turn it around? A is now assigned to be 0. So what's the truth value of 0? Truth value of 0? False. And not A? True. And trying to print true as an integer, what's a reasonable thing for it to do? Yeah, so this is kind of a choice that it makes, right? It'll print 1. Oh, I didn't save. I hope I'm not saying something wrong. There, okay, good. Right, so prints 1. This is just a tricky thing, right? And the whole point of this exercise, 2 arguments. One, all numbers have a truth value associated to it. By default, the way you can think about it is zeros mean false, anything else means true. And then when you have logical operators operate on the truth value of things, in contrast to the bitwise operators. So is any of this different versus Java? This is exactly the same in Java, right? All these rules that I just reminded you are also true in Java. Again, Java descended from C. Okay, so that recaps and concludes bits and bytes. Any kind of closing thoughts and comments and questions before we move on to actual numbers? Yeah.
When you declared but didn't initialize the unsigned int a, why was that true when it didn't have a number associated with it?
That's a good question. And I'll be honest with you, I don't know what's the rationale. Right? You're asking about this case. A is declared but not initialized, and yet we query what's the truth value of something uninitialized, and it considers it to be true. I don't know the rationale, to be honest. We can check the language manual and see what it has to say about it. Okay, any other questions before? Yeah, go ahead.
Question which was not on this was on the previous stuff when you were going like over hexadecimal, octal, and binary and stuff. Besides like base 10, base 2, base 8, and base 16, in C, like how do you write a number of like n base of like your choosing? Like could I like write a number of like base 5?
Okay, so the question is in C, we've demonstrated the option of writing numbers in different bases, right? So we can repurpose this code to do so. So I want to print the number 255. I can declare it as decimal. There it prints 255. What are other ways I can specify this number? What if I wanted to write this down as binary? Yeah.
We do %b for it.
%b, okay. That's an interesting approach. Does that work? No, it doesn't accept that. Yeah.
Not like in there, like it would be like 0b a.
Yeah, so that's what I'm trying to get at, right? So I want to specify this number. I want to write it down as a binary number. This is equivalent for me to write 0b, and what's the binary representation of 255? What's special about 255? Yeah.
It's 1 before 2 to the 8. So is it 8 ones or 7 ones?
So it's 1 before 2 to the 8. Exactly, right? 2 to the 8th is 256. 256 minus 1 is 255. And how do we write 2 to the 8th? 1 followed by 8 zeros. Right? So that's 1 followed by 8 zeros. But we're not writing this number down, right? I want to print 255 again. So how do I get to that? Yeah.
Get rid of the 1 and change all the other zeros to 1.
I decrement by 1, right? So 255 is just 8 ones. So me typing this code, compiling it, is going to print the exact same thing, 255. What's another way? I think I can think of 2 more ways to keep going. What's the next one? Somebody else, maybe in that side of the room? Where are we heading with this? Yeah.
You just put a 0 in front of the number. So like 0, 1, 5.
Okay, so the claim is if we wrote 0255, what's the gotcha here? You know, I aesthetically, you know, I like 4 digits, right? So just as kind of a habit, I emphasize that this is 0255, 0255. And what's the terrible gotcha that you've just stumbled into? Yeah.
It's going to end up as an octal number.
Yeah, a very unfortunate and I think at this point very outdated design choice of C is when you put this 0, it has catastrophically treated this as an octal number. Right? It's very unintuitive. It may have made sense 50 years ago for some reason, but at this point, a lot of languages have gotten rid of this feature. Right? Python won't let you fall into this trap, for example. Java will still. So what's the octal representation of 255? Yeah, back there.
377.
Yeah, it's 377, right? 3 times 2 to the 8 to the second power, so 3 times 64 plus 7 times 8 plus 7 is 255. So we can convince ourselves, yep, that prints 255. And what's the fourth and last way that we can do this? Yeah.
Hexadecimal?
We can do hexadecimal. So how do I write a hexadecimal? Yeah, just shout it out.
0x.
So YFF. So F is 15. So 15 times 16 plus another 15 is 255. Okay, so your question was, are there other ways to write numbers? If I want to write numbers as base 5 for some reason, is that supported? No, it's not supported, right? So the only ways that are supported are base 2, base 8, base 10, base 16. Yeah.
Can you do that in Java?
I believe everything mentioned here so far is all valid in Java too. That's right. Oh, could you write base 5 in Java? Probably not. It's not a native language feature. But again, right, you can double check. Okay, let's rewind here. So any other closing comments about bits and bytes? And all that is good. This is good review for what we need to do next, which is integers and representing signed integers. Okay, so what we need to do next is a discussion about how do we represent signed numbers in C, and also in Java, actually. Right, so maybe just recap, right? In Java, do we have to worry about signed and unsigned? So some head shakes, right? By default, in Java, so what happens instead? If we never have to worry about whether a number is signed, what's the default in Java? Yeah. Yeah. Yeah, by default, numbers in Java, I believe, are all signed, right? You can always represent the number being positive or minus. In C, there's now a distinction, right? A number could be signed or unsigned. And if a number is declared to be unsigned, it will always evaluate to be a positive integer. So the task that we have to do now is, so what's a correct systematic way to represent negative numbers? And what are some trade-offs? So in day-to-day life, right? In day-to-day life, I want to represent a number as negative. I have 255, and now I want to represent the negated value of 255. 255 less than 0. How do I describe that? Yeah.
Could you use that first byte to show positive or negative for that first bit?
So you would like to use the first bit to represent positive or negative, right? So in day-to-day life, when I want to write a number as its negated number, our convention is we have this thing called a sign symbol, right? And in computers, everything is all binary. So one approach is maybe we can dedicate a bit to indicate a number is negative. Good. So that's exactly the first choice that we'll think about. So let's do that, right? So what we'll do now is think through the pros and cons of such an approach. And for this whole exercise, what I'll do is all the numbers that we'll study is what can fit in a single byte. 1 byte. If I got 1 byte, and I'm going to dedicate the first bit to represent the sign, what's the smallest number that we can represent, the most negative number we can represent? All right, what would that number look like? Yeah. So category 1, most neg number. So I want to represent the number to be negative. So what's our choice that we can do here? Yeah. So we'll dedicate, right, like we said, we're going to dedicate the first bit to be, represent that this is a negative number. So now we're talking about negative numbers, and I want the most negative number. What's our next choice? Yeah. It's going to be negative 2 to the 7. Close, not quite. Yeah. Getting colder, not that either. Yeah. Negative 127, how do you figure that?
Because if you have 8 bits in a byte, you use the first one, then you only have 7 more bits to use, so you do 2 to the 7 minus 1.
Yeah, so the most negative number that we've got here is the first one indicates, yeah, it's a negative number. And then the remaining 7 bits. Why 7 bits? Because I'm considering what can you do with a single byte, right? 1 byte is 8 bits. So the remaining 7 bits, I call them all ones. So this is the most negative number we can represent in this representation. And what does that correspond to? This is minus 127. Okay, what's the most positive number we can represent? What's the first bit going to be? Yeah, 0. And how do we get to the very most positive number possible? All of them being 1. Right? And what does this evaluate to be? This evaluates to be positive 127. How do we represent some other important numbers? How do we represent 0? How do we represent 0? Yeah. Okay, all zeros, yep. So 0, 0, 0, 0, 0, 0, 0, 0. That definitely represents 0. What other thing will evaluate to be 0?
Would 1, 0, 0, 0, 0, 0, 0
Yeah, so you could argue that this thing will also be the same value, right? It's got a negative sign, but the magnitude is 0, so I would think that's also a 0. So we've got some redundancy. I've got 2 ways to write down the numerical value of 0. And how do we write positive 1? It's a positive number, so positive 1, just to be clear, is that. And negative 1 is going to be 1, 0, 0, 0, 0, 0, 0, 1 is negative 1. And there you go. Positive 1, 0, and minus 1. So those are some important numbers. This is all very good. What's the first operation that we'd like to do? What are a couple of operations we'd like to do when we have a number system? Yeah.
Adding and subtracting numbers.
Okay, you would like to add and subtract. That's good. What's even more fundamental than adding and subtracting? Yeah. Comparing. Okay. So we can compare numbers, no problem. Right? Sure, right? I can make a little point here, which is if I wanted to compare numbers, say I want to compare 0, what's like a downside already that this has encountered? I'm going to compare 2 numbers that we've agreed are just 0. right? And what's going to happen here, right? So this is kind of subtle, right? We think that 0 should equate to 0 numerically, but the fact that we have two numerical representations, binary representations, kind of gums up the works, right? It's unintuitive. These two bit strings, they're different bits, but numerically they should be the same value. So I've made a little point about comparing. The next fundamental operation that we need to think about is negation. So does negation make sense here? I've got positive 127, and I'd like to negate it. What's the operation to negate it? Yeah.
Just flip the first bit.
Yeah, so if I want to I want to negate positive 127, well, that is just a matter of taking positive 127 and flipping the first bit. No problem, right? So negation works pretty well in this system. It's just a matter of flipping the first bit. And finally, right, the third important operation that we're interested in is, as you said, adding and subtracting numbers, right? So we would like for addition and subtraction to be sound. So let's take a very simple example here, right? I want to add -1 to +1. I want to add these things together, right? And already I've got on the board my representations, right? So what's the representation of -1? That's the representation of -1. And I've got my representation for +1. And what's my desired result? Right, so what should -1 + 1 be? It's 0, right? So that's what we're trying to get to. And what's the representation of 0? Say we pick one of them. Right? We want to somehow arrive at least one of these, right? I want to somehow do an operator that results in this. So what's a reasonable way to make this work? Trick question, right? It's really tricky, right? I've got this representation, which is -1. I've got this representation, which is +1. Somehow I want to have some kind of sensible bitwise operator to get this to add up to be correctly 0. And there's no obvious rule, right? If I just did a naive thing, which is I performed bitwise add on these two numbers together, right? I perform bitwise operations. I add in the normal way. I add in the intuitive way. What will this become? I've got ones in the ones digit, so what that becomes, I've got 0 in the ones digit, I carry 1, and I've got 0, 0, 0, 0, 0, and then I've got the sign bit, which here I'm going to try to add them together and write that down. What does this evaluate to according to our convention? Yeah, this says it's, well, there you go. We've got -2, boss. No good, right? Adding in the normal way makes no sense here, right? Yeah, comment. Yeah.
So couldn't you like say if like you first compare the first two bits, right? If they're the same, then you add the normal way. But if they're different, and then like if they're different, then you do like something else. Like in this case, this is 1, 1. They'll like each go to 0.
Yeah, so what you're proposing is, okay, maybe one way we could make this to work out is first let's look at the sign bit, and if they disagree in sign, then do a certain set of rules so that addition makes sense, right? And already that's way too complicated, right? It's unnecessarily complicated. The point I'm making here is this encoding sucks. We're not going to use this encoding, right? Because even though comparing has some has some favorable properties. Negation makes sense, that's good. Negation is good. Addition is not gonna work in the normal way, right? So this is a straw man approach to show that, okay, approach one of using sign magnitude is not a good design. So what we'll present next is a couple better alternatives. The first alternative is called one's complement, right? And the way that one's complement is, if I want to negate a number, I just flip all the bits. That's it, right? And it's called one's complement, plural one, so a bunch of ones, and complement. So that's what one's complement means. Take all the bits, flip all of them, and you get the negated number. So let's consider this number system. One's complement flips all bits to negate a number. And here, we're gonna see some properties. So we're gonna make all the same set of notes as we had before. So this set of notes is about one's complement. So what's our methodology here? I want to first write down for what you can store in a single byte, what's the most negative number? How would I represent the most negative number possible? 8 ones. So what happens if we write down 8 ones, right? Let me just double check. Okay, what happens if we write down 8 ones? So maybe it will detour a little bit, right? How would I write down 0 in this representation? Yeah. So yeah, so writing down zeros is going to give us the representation of 0. And remember our rule, right? The rule that we're following right now is if you flip all the bits, then you get the negative number. So if I flip all the bits in 0, what does that give us? 8 ones. And this is also a 0, right? This is another representation of 0. Okay, so the most negative number is not 8 ones. So is it 8 zeros? No, 8 zeros, again, dedicated to be representing 0. So maybe let's come over here, right? What's the most positive number we can write down? Yeah. 1, 1, 1, 1, 1, 1, 1, 0. Not quite. Yeah.
Is it just 1 at the beginning followed by the rest of zeros?
1 at the beginning followed by a bunch of zeros? Not quite either. Yeah.
Is it 0 followed by 1s?
Yeah, so the answer is the most positive number we can represent here is a single 0 followed by 7 ones. So why define this to be the most positive number? Right? The convention here is still, we would like to use that leading bit to represent if it's a positive or negative number. So in a byte, if your representation type is 1 byte, we'll dedicate this representation to mean the most positive number. It's most positive because the first bit is 0, meaning it's a positive number, and the rest, we dedicate it to representing the largest magnitude possible. What's this numerical value? Positive 127. Good. And you can convince yourself that that's the case, right? That is 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, 127. So we're zoning in closer now, right? So what's the most negative number we can represent? So we want to follow the convention where the first bit, if it's 1, represents a negative number. So the most negative number is definitely going to begin with 1. And what's the most negative number we can possibly get? Yeah. Negative 127, what's that representation? It's 1 followed by 7 zeros, right? This is negative 127. Good. Okay, so what are some things we want to do next? Right, so this is how it's defined. I can write down a couple other important values. We were interested in what's the representation of positive 1, negative 1. So how do I write down positive 1? Right, positive 1 is going to start with a 0, indicating it's a positive number. And if I want to get negative 1, what's the rule? Yeah, flip all bits, right? Flipping all bits gets us negative 1. So how do I flip all the bits here? So I've got positive 1 written down here, no problem. If I flip all bits, it's going to be 1, 1, 1, 1, 1, 1, 1, 0. That is the representation for negative 1 for this number system. Okay, so the 3 different operations that we're interested in, right? Now that we've devised encoding, we're interested in building a sensible set of rules to, I think we did several of them, right? Compare, negate, and add, to add numbers. So let's consider comparing numbers, negating numbers, and addition. So what can we say about comparing numbers here? Well, comparing equality is the same, right? I can take 2 numbers. If they are equal in value, positive 127, their bit strings will represent the same thing. But there is a tricky thing where I've got 2 representations of 0. Which you could say is a little bit of a downside, right? There's 2 ways to write down 0. That's unintuitive. What about negating? What's our rule for negating? Yeah. Yeah, so does negation work soundly? Yeah, no problem, right? Our exercise was, I would like to write down the negative number representation of plus 127. And the way we would do that is you take 0, 1, 1, 1, 1, 1, 1, 1, which represents positive 127. We follow the rule. Negating numbers goes by flipping all bits. And indeed, that is what's being correctly represented, right? So positive 127 there. When you flip all bits, you do get what you expect, which is negative 127. And addition. So what was the work example that we did for addition? Yeah.
In this case, addition would work like when you add like 2 like 1, so do like normal, or if you add 1 and 0, like say 1 and 0 would work. Because like in this case, negative 127 plus positive 127 would equal all 1s, which would get 0.
Okay, so the claim is addition works straightforwardly. So I'll let you guys pick what to test out here. So what should we test out to show that addition works in a normal way? Yeah.
We try to like negative 25 plus 25 because it's not one of the traditional numbers we use.
Let's start small, right? Let's just do positive 1 plus negative 1. What does that give us? So negative 1 I got -1, and I want to add that to +1. The binary representation of -1 is this. I will add that to the representation of +1 there, and addition in the normal way, right? I go by bit, and I add. So what will this result in? All ones. And how do we interpret this string of bits, all ones? It is one of the representations of 0, right? It's one of the correct representations of 0. Okay, so it seems like, okay, that's good. Addition seems to work in a normal way. What else should we try? There's a corner case here that we're trying to hit. Yeah.
If you add numbers of different magnitudes, like if you add a positive number, that's a bigger magnitude than the negative number.
Okay, so if we want to add a positive number,
Like for example, like positive, like
say +2.
like positive 100 and -5.
So you want to test +100 and -5. So let's simplify a little bit, right? Let's just do +2 minus 1. Should we try that? So what's the representation for +2? Representation of +2? It's going to start with a 0 because it's a positive number. And 2 is simply going to be a 1 in the 2's digit. And the representation of -1, so it starts with a 1 because it's a negative number. And then we've written it down, right? So the representation of -1 is going to be that string there. 1, 1, 1. 1, 1, 1, 0. Okay, so what do we expect? We would hope that +2 minus 1, or +2 plus -1, gives us 1, right? That's what we hope. So if we do addition in the normal way, what happens? All right, let me write this down as a format that's easier to work with. Addition in the normal way. So I go bit by bit. So I've got 0 there. 1 plus 1 equals 1. Carry 1. 1. Carry, oh, no, not carry 1. Back. 1 plus 1 equals 0. Carry a 1, gets a 0. Carry a 1, gets a 0. Carry a 1, gets a 0, 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 and 1 extra over there. So something tricky has happened, right? If we do addition in the normal way, what does this evaluate to? Yeah.
0. Well, because like we're only using 1 byte, so the value is 0.
So if we do addition in the normal way, 1 plus 1 equals 0, carry 1. I've got a string of all zeros. I've got a string of all zeros. And this, well, this evaluates to, what does that evaluate to? That's one of the representations of 0. Right, so how do we fix this up? How do we fix this up? And this is a kind of subtle thing, right? Addition in 1's complement works fine. There's a very special rule, though. The special rule is if you have a carry out when you do addition, this carry has to wrap around. So this is called carry wraparound. If I did this addition in a normal way, add, I carried 1 out the front, this has to be added back, right? Because of that 1 that carried out, I need to fix it up by adding 1 to get addition to work soundly. Right? And I'm just going to emphasize that there. This is called carry wrap around. Carry wraparound. Right? Any questions here? And we could do more examples. We can convince ourselves, yeah, if we follow this set of rules, addition in 1's complement works fine, just like normal addition. With this special rule, then addition works fine. Right? So what are some pros and cons? So pros and cons between these two so far. Again, right, this is kind of not just about learning what it is, but really everything here is a designed thing. Right? Everything is kind of motivated by what's good design. So what are some pros and cons between the two that we've thought about so far? So pros of sign magnitude. Right, we can summarize on this slide here. Pros of sign magnitude approach. Yeah.
It's intuitive.
Okay, intuitive, that's always good. What other pros? I would say that's about it. That's the only thing going for sign magnitude is it's our first idea, right? And immediately we saw that there's some cons to it. The biggest con was what? Yeah.
You can't really perform arithmetic with it.
Yeah, add doesn't work. Addition is weird. Addition weird. I'll summarize as that, right? So instead of that, we tried the next idea, which was to flip all bits. Maybe that can help us encode 1s. And what are pros of that? So it's a little bit less intuitive, right? So it's still intuitive, sort of intuitive, sorta intuitive. And is addition working normally as expected? It's nearly good, right? Addition nearly works with one strange rule, that there's this additional carry a wraparound rule. So the summary I'll put down is addition is also sort of weird, right? It has this additional rule to it, right? All of this is leading up to what we'll do, I guess, not today, because we're running out of time, which is our next idea, right? Our next idea, which is the 2's complement approach. So what are we trying to get at? We want an approach where addition works perfectly with no additional rules. We want to have something where that addition works perfectly fine, right? So we're not quite out of time, so maybe we can get a little bit started on 2's complement. And 2's complement is a set of rules where the rule for negating a number is done by flip all bits and add 1, right? 2's complement, flip all bits and add 1. So we can do the same exercise as before, right? Given 1 byte of storage, we would like to write down, as emphasis, the most negative number, most positive number. We want to write down 0, and we want to write down +1, and -1. So what should we do first? You can just shout it out, right? What should we do first?
0.
All right, let's do 0, right? So how do we write down 0? Yeah.
So it'd be all zeros except 1 at the end?
Nope, that's 0.
No, except 1 at the end.
Except 1 at the end. Why is except 1 at the end?
Because you are flipping all bits and adding 1. So 0 would either be that or you flip it and add 1. Followed by all zeros.
So we designed 0 to be this, right? We defined this to be 0, right? 0 so far in every case study we've done so far, 0 has been written down in the normal way, right? No matter in the sign magnitude form, in the 1's complement form, and also now in the 2's complement form, we're going to write down 0 in this way. How do we write down 1? Yeah.
Just be regular 1.
Yeah, just regular old 1, right? And the rule for representing negative numbers, right? What's the rule? Flip all bits and add 1. So we can now write down -1. So the way we write down -1 is we flip all bits from +1. So 1, 1, 1, 1, 1, 1, 1, 0, but it's flip all bits and add 1, right? So this is the representation for -1. How do we write down the most positive number possible? Yeah, back there.
0 and all 1.
Good. So you propose 0 and all 1s. So why 0 at the beginning? Right, we're appealing to a design choice, right? We want all positive numbers to have a leading 0, right? So that we can see immediately right away, yep, it's a positive number. So if we dedicated that first bit to encode sign, well, given a single byte, the largest, most positive number is going to be 0 followed by all 1s. And what's that numerical value? Seven ones. Yeah, it's 127. We talked about that already. And so what's going to be the most negative number possible? Yeah.
-128.
How do you figure -128?
Because the 0 is the first digit is the 0. So that means there's going to be no 0 with a 1 in front of as the first digit. So that means there's 1, 1, also 1.
So I'm not going to let you get away with that so quickly, right? So I'm going to work through this pedantically. How do we get to -127? Yeah. So I want to write down -127. So I've got +127 written down here already, very nicely. So I'm going to write down -127. So the rule is flip all bits. So I got 1, 0, 0, 0, 0, 0, 0, 0, and add 1, right? Flip all bits and add 1. So that's -127. And then that begs the question, right? What was that thing I written down at first? What was this thing? 1 followed by all zeros, right? This is going to be defined as the most negative number, -128. And so what's the peculiar thing that we've noticed now? So first of all, are there multiple representations of 0? If I flipped 0, negated 0 and add 1, negating 0 and add 1, right? If I had flipped all bits of 0, I flipped all bits of 0 and added 1, that gets us 0, 0, 0, 0, 0, 0, 0, 0, and carry 1, right? the remaining bits, that still represents 0. So how many ways are there to write down 0 now? Just one, right? We no longer have a redundant representation of 0. And what's the other peculiar thing I just want to point out before we let go? Yeah.
Because 0 starts with 0, it's represented as a positive number, therefore there's like a larger
No,
one more.
that's one thing. So we got to name the elephant in the room before we can let out. What's the elephant in the room?
Most negative number from this one is -128.
Yeah, the most negative number is not the same magnitude as the most positive number, right? This is a cool thing. We've removed the redundancy of representing 0, and instead we allow us to represent one more negative number, right? That's another characteristic of this. So this is one approach to derive 2's complement. We'll come back on Tuesday again, and we'll study this in some more. There's another trick to it, which is just to look at that and think of that as -128. All right, so we'll leave it at that.